probability of getting at least one heart if you're dealt 5 cards. Okay, so the way I wrote it is actually for if order mattered, because you have 39 times 38 times 37 times 36 times 35 divided by 52 times 51 times 50 times 49 times 48. Okay, so we actually don't want that way. Okay, so let me erase this then. All right, so the way we want to, at least when we still want to do 1 minus. Okay, but because order doesn't matter, we need combination in here, right? Because you're just getting a hand of 5 cards, right? It doesn't matter the order of them anyway. So the way we want this is 1 minus, well, how many ways can I get the 5 cards? So no hearts, there's 39 cards that are no hearts. You want to pick 5 of them and divide it by the total number of ways you can get 5 cards, which is 52, choose 5. And that's what you want. I didn't even multiply this out, but that's what you want your answer to be. All right, so change that in your notes. I'm gonna re-upload this with the correct answer. Okay, but this should be your answer for that one. All right, any questions on that one? Everyone see the difference? The 39 is the number of cards that are not hearts that you're choosing from. All right, any other questions on that one? We have one more probability section, so 7.2, and then we will move on to something else, chapter 8. All right, so 7.2. Oh, before I forget, so after you play around with LaTeX and you figure things out, if you start, so you can start using it to type up your homework if you want. Okay, if you do that, I'm gonna start giving you guys like 2 extra points on every assignment that you type up. So you could be getting extra credit that way if you want to put your grade up. All right, so 7.2, so some more probability. Okay, so from 7.1, we learned that the probability of something happening has to be between 0 and 1. Right? 0 being impossible, 1 being for certain. Right? It can't be anything less than 0, it can't be anything greater than 0. Okay. What we also know is that the sum of all these outcomes has to be 1. Okay, so the sum of probabilities of all possible outcomes is 1. Okay. So it's like if you think about rolling a die. So a regular 6-sided die, right? You got the numbers 1, 2, 3, 4, 5, and 6 on there. Right. The probability, if it's fair, of any side coming up is 1 out of 6. So 1 out of 6 for each of them, that's 6 times, that adds up to 1. Okay, if it doesn't add up to 1, something's missing. If it adds up to more than 1, something's wrong. All right, so let's look at a coin example. So what probability should be assigned to the outcomes? Heads and tails when a fair coin is flipped. Okay, so I mean, with the fair coin, we know the probability of heads is 1/2, and the probability of tails is 1/2. Right, those are all your possible outcomes, right? There are no other outcomes that are possible when flipping a fair coin, right? It's either heads or tails. So probability of heads plus probability of tails, well, that should come out to 1 according to what we just did. All right, we get 1/2 plus 1/2, that is 1. All right, any questions on that one? Actually, just with the stats class earlier, we talked about flipping coin, and Stanford actually did an experiment like 15 years ago on that. The probability is actually higher of a coin landing on the face that you started with. So if you're holding it like with heads up and you flip it, the probability is actually a little bit higher that it's going to land on heads, which I thought was really interesting. But that involves a lot more physics in it, on being able to flip it with the same force every time. All right, so let's look at part B. So what about a coin where heads comes up twice as often? Okay, so it's not fair anymore. Okay, so now heads is coming up twice as often as tails. Right? Either way, we know the probability of heads plus the probability of tails has to be 1. Okay. Either way, they still have to add up to 1. Now, you can think about it in a couple of ways. You know, heads is twice as often as tails. So, I mean, you can use x if you want. Right? Twice as often. So 2x plus x has to equal 1. Yeah, that's right, Willie. This is 3x equals 1, so x is 1/3. Right? X, remember, we labeled as the probability of tails. So probability of tails is 1/3. Probability of heads is 2/3. Right? Twice as often as tails. Well, this is twice as often, right? And it adds up to 1. There's no other way for you to do that, where you only have heads and tails and it's twice as often.
Wait, so I understood how we got the 1/3, but I don't know where we got the 2/3 from.
Well, because heads is twice as much as tails.
So you just added a 2 to that one?
Well, it's twice as much. So tails is 1/3, twice
Yeah.
as often, so times 2.
Oh, I see. All right, for
Yeah.
sure.
All right, any questions on that? All right. And then the next thing is uniform distribution. So uniform distribution is where all the probabilities are the same. So like in a fair die, in a fair coin, right? It's all one out of and then how many outcomes there are. So like when we talked about the die one, there's 6 possibilities. If it's fair, then every single one of those probabilities is 1 out of 6. Okay, so that is what we call a uniform distribution. Okay, the probability, and then the second thing, the probability of the event. E is the sum of the probabilities of the outcomes in E. Okay, and we'll see an example of that right now. All right. Sorry, I'm trying to mark off who's here. Side note, I kind of cleaned up our Canvas page, so hopefully you guys saw that. If you go to like announcements, you should be able to see all the links to, so to this, to the Zoom meeting, to the YouTube videos that I put from chapter 3 and chapter 5, and then the YouTube videos that Lev is putting up also. All right, so let's look at this example here. So suppose that a die is loaded or biased so that 3 appears twice as often as each other number, but that the other 5 outcomes are equally likely. What is the probability that an odd number appears when we roll this die? Okay, so we have a biased die, right? So there's 6 sides, but in this case, the 3 appears twice as much as every other number, okay? And every other number has the same probability of showing up. All right, so let's kind of break this down into pieces. All right, so in this case, we kind of label it how we had up here in our definition, right? The event E, well, in this case, our event E is, we want an odd number to appear. So the only odd numbers on a die are 1, 3, and 5. Okay, so we want the sum of the probabilities of those outcomes. So the probability of getting 1 plus the probability of getting 3 plus the probability of getting 5. Right, this is the probability of an odd number. All right, so let's figure out what these are. Okay, because it's not going to be 1, 6 and 1, 6 and 2, 6. Okay, now there's a few ways to think about it. So typically, you have 6 options, right? You got 1, 2, 3, 4, 5, 6. Right, those are all the things that can pop or can come up with when you roll a die, and they're all 1/6 of a chance. Now the difference here is that 3 appears twice as often. So the way you think about it is, okay, well, you actually have another 3 now in there. Okay, every number comes up once, 3 comes up twice as much. All right, well, how many numbers are you dealing with now? You no longer have 6 numbers, right? You now have 7 things to look at. Right, so every probability is going to be out of 7 instead of 6. Now the probability of a 1 coming up, well, there's only one 1 in there, so 1 out of 7. Right? The thing that's different now is the probability of a 3. All right, 3 is, there's 2 3s now, right? Twice as much. So 2 out of 7. And then a 5 is 1 out of 7. So adding those together, the probability of an odd number is 4 out of 7. All right, any questions on that? All right. So next thing then, we have a theorem and a definition. So a theorem, if E sub 1 comma E sub 2 is a sequence, and then dot 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 is a sequence of pairwise disjoint events in the sample space S, then the probability of all those happening is the sum. Disjoint means that they have no effect on each other. Okay, or they don't overlap. Okay, there's no effect on each other, they don't overlap. They're independent. It's another way to think about it. Okay, so it's just like looking at this one above here, right? We added those 3 up together because they didn't affect each other, right? 1 doesn't affect you getting a 3, 3 doesn't affect you getting a 5. Right, they're independent. Okay, and the definition is if E and F are events with the probability of F being greater than 0, the conditional probability of E, and then when you think of conditionals, you look for that word given. Okay, so E given F, and this is the notation it has that vertical line. And we define that to be the probability of the intersection divided by the probability of the given part. Okay, so when you have that given, it's like literally like you're given more information. Okay, so it kind of changes your denominator. All right, so we're going to see some examples about that right now. All right, so example, what's the probability that a family with 2 children has 2 boys, given they have at least 1 boy? Assume having a boy and a girl are equally likely. Okay. So let's look at first off, what are our possible cases? Well, we got 2 kids, so you can have a boy and a boy. You can have a boy and a girl, which boy, we'll just say in this case, that means that the boy is older. You can have a girl and a boy, and a girl and a girl. Okay, so in this case here, it's saying older boy, and then the third one, it's that the girl is older. All right, so let's look at what do we want? So we have probability that a family has 2 boys given they have at least 1. So those are your 2 events. All right, so we'll call them E. Okay, so E, let's just say, so the way we wrote it, I'm gonna match it up with the definition. So E given F. Okay, so the E is 2 boys. So there's only one way to have 2 boys. Okay, but with F, we'll say F as at least 1 boy. So you can have boy, 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 girl, or girl, boy. So this is at least 1. At least 1 boy. All right, so now I'm going to use this formula, and I kept E's and F's the same. Okay, so the probability of E given F. Okay, so that's the probability of getting 2 boys given you have at least 1. That is the same as the probability of the intersection divided the probability of the given. All right, so I mean, we can write down what the intersection is. All right, so the intersection is what's in both. Well, there's only boy, boy in this one, boy, boy in that one. So the intersection is boy, boy. Now the probability of getting that, well, that's 1 out of 4. So we get 1 out of 4 divided by the probability of getting something in F. F was this set here. There's 3 of them in there. So 3 out of 4. So 1 out of 4 divided by 3 out of 4 is 1 out of 3. Yeah, Chris, that's what Andre's saying. It can be, Caesar. Not a direct relationship, but it can be. There's some biological things in here that, can change because I don't think it's equally likely to have a boy and a girl. I think it's a little bit different. All right, I don't think it's 50-50. But just for the sake of doing this example, yeah, it's a 51% for a girl. And it was a little bit different. But just for the sake of this problem, say equally likely. All right, we're gonna build on this right now. So another definition. So E and F are independent. Okay, so I kind of use that word up here, right? But independent, exactly what you would think independent to be, right? Where the 2 events don't affect each other. Okay, if and only if the probability of the intersection is equal to the probability of each one of those events multiplied together. Okay, Now, if you kind of match it up to this formula here, right, that would be, these almost look the same, right? You got that intersection, but in this first one, you have it divided by P, the probability of event F. Well, if you divide that over, you get the intersection divided by that probability, right? So just dividing both sides by the probability of F. Now this is pretty much looking like this formula up here. Now the difference is the given part, right? So what you're actually asking for with independence is, does the probability of E given F equal the probability of just E, right? Now think about what that means, right? The probability of E given F. So me telling you something about F, does that have any effect on the probability of looking at E, right? That is what it means to be independent, right? So, I mean, you can, in a regular context, like a nice one, does the probability of flipping a coin and getting tails equal the probability of getting tails given that you got a heads before. Right, so we know with coin flipping, they're independent, right? The flipping of getting one, heads or tails, it's not affected by what happened before, right? So that's a way to think about it also. Okay, but in a sense, this is what's happening, right? Do those two probabilities equal each other? Right? If they do, then it is independent. If they don't, then it is not independent. Okay, so with the same example here, let's look at this. So are the events E that a family has two children, has two boys, and F that a family with two children has at least one boy, independent? So looking at this previous example. Okay, well, we have the same E and F, right? E was, the probability of E was 1/4. Probability of F was 3/4, right? Using the same E and F from before. Right, so does the intersection equal the probability of each individual one multiplied together? Right, well, we know that we did this, the intersection was 1/4. This right side, well, that's 1/4 times 3/4. 1/4 does not equal 1/4 times 3/4 is 3/16. Right, so not independent. Right, so by telling you that given part, right, that given part in this case that the family has at least one boy, it changes it. Right, it changes to finding the probability that that family has two boys. Which is kind of weird to think, right? You would think they would be independent. Any questions on this one? Not necessarily increases, but that it does have an effect. All right, a couple more things in this section. This next example, a little bit not really tied to what we had, but I wanted to squeeze it in there. So suppose we have a biased coin, so the probability of getting tails is 5/8. What's the probability of getting exactly 3 tails when flipped 5 times? All right. So, you have you want exactly 3 out of 5 times. Okay. So we're going to kind of tie chapters 6 and 7 in here, right? You have your 5 spots, right? Your 5 flips, right? We need exactly 3. So without any probability stuff in there, well, we would say, well, how many ways can you have exactly 3 tails? Right, so that's combination of 5 choose 3. Right, you need to pick exactly 3 tails. Okay, once you pick those, the heads fall into place, right? You have then 2 choose 2, which is just one way. Now invoking probability, right? Well, for each one of those tails, the probability is 5/8. So you get 5/8 for one, 5/8 for another, 5/8 for a third. So that's to the third power, right? 3 of those tails. And then you also need the heads to happen. So if 5 out of 8 is the probability of getting tails, then 3 out of 8 is the probability of getting heads. And you have 2 of those, so squared. Thank you, Willie. Yeah, I didn't write what this was, but 0.343. Okay, this right here is an example of a Bernoulli trial. Okay, Bernoulli trials are where there are only 2 outcomes. Okay, so in this case, heads or tails. Okay, there's a formula to find all these, but it's the same exact thing here that we talked about. All right, I don't really stick to formulas too much. Right, it's more just thinking about it. Right, pick where those things go and the probabilities of each. Right, notice that the exponents, they have to add up to the number of spots. Right, that makes sense. The probabilities, those should add up to 1. Right, also makes sense. All right, so 2 questions. So the 5 choose 3. Yeah, you want the exactly 3 tails, Andre, so you gotta pick where those 3 are gonna be. And Misal, the 3/8 comes from, that's the probability of getting heads. So it's 5/8 to get tails, 3/8 has to be to get heads, right? Because they have to add up to 1. Any other questions on that one? There's a formula in your book, but like I said, it's the same exact thinking. All right. Yeah, last thing then from chapter 7, random variables. Okay, so random variables is a very misleading term for what this actually is, because they're not really random and they're not really variables. But a random variable is a function from the sample space of an experiment to the set of real numbers. A random variable assigns a real number to each possible outcome. Okay, so I think it's better to see this with an example, and you'll see what random variables actually are. Okay, so like I said, not really random and not variables. But suppose we have a fair coin flip 3 times. Let x sub t be the random variable that equals the number of tails that appears when t is the outcome. Okay. All right, so if we are flipping a coin 3 times, how many possible scenarios are there? So you can have heads, 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 tails, tails, tails. How many scenarios are there? You're flipping 3 times. Yeah, 8. 2 to the third, right? 2 options for each spot, right? Heads and tails, 2 times 2 times 2, 8. Okay. So what this says is our function, right? So we'll do all 8. So we can have heads, heads, heads. We can have tails, tails, tails. We can have heads, tails, tails. I'm doing this in no specific order, which is usually not the way to go, because I'm going to not know which ones I have left. What am I missing? Heads, tails, tails. All right, and that should be it. All right, I think I got all, no repeats. All right, so this random variable, right, equals the number of tails that appear when t is the outcome. Okay, so t was my outcome, so these were my 8 outcomes that we had, right? We said there was 8 scenarios, so my 8 outcomes. Did I repeat one? Oh yeah, I did. HTT, thank you. I'm missing tails, heads, heads. Thank you guys. Okay, so my 8 outcomes. Now remember the number of tails that appear. Okay, so in this first one, HHH, right? Number of tails in there is 0. Okay, this third one got 3 tails. And then I have 2 tails, I have 1 tail, 1 tail, 2 tails, 2 tails, 1 tail. Okay, everyone cool with that? So what is the probability of each outcome? Okay, so now the way we write these, so you guys can see they're all equally likely of each, right? Now, the way you kind of write this is, okay, so the probability, and the way we write it is like this. So x equals 0. Now that x being 0 is saying, in this case, 0 tails, right? You're also going to have the probability where x is 1, the probability where x is 2, and the probability where x is 3. Right, so for the 0 case, well, only 1 time out of 8 did we have 0 tails. This is saying 1 tail. So I got 1, 2, 3, 1. So 3 out of 8. 2 tails. I got 1, 2, 3. So 2 tails there, or 3 of the 2 tails. So that's 3/8. And now if you kind of think about, right, all these probabilities should up to 1. Well, I got 3/8 plus 3/8. That's 6/8 plus 1/8 is 7/8. So this one better be 7/8 or 1/8, right? Otherwise, something's wrong. 3 tails, that happened once. So 1 out of 8. All right, any questions on that one?
So if we want to like get all the outcomes of heads and tails, do we have to split them out just like you did, or do we have another way to do it?
Well, you know there's 8 of them from counting,
Right.
right? You can count all of them. You know, like how many have exactly 2, how many have exactly 1. You can do it that way. So like, you know, where this 1 comes from. So like this is exactly 1. Well, you have 3 spots to choose from. You got to pick one of those to be the tail. So that's 3, choose 1, which is 3. Same thing with this. That'll be a 3, choose 2, which is 3 of them. 3, choose 0 is 1. 3, choose 3 is also 1. So, I mean, you can do it that way too.
All right, appreciate it. Thank you.
Mhm. All right, any questions on that one? I want to end. I didn't want that same page. Dang it. I forgot how to delete pages. But let's do blank one. Okay, so I want to end this chapter with actually doing the probability of two people having the same birthday. All right, so we did this. Did I do this with you guys in class? I don't remember.
Yeah, I think you did it the first day of class.
The first day? And did it work?
Yeah. What's that?
Did it work? Did two people have the same birthday? I don't remember. I've done this for every
Yeah.
class. It did?
No, I don't
No?
think so.
Oh yeah, because you guys had like 35 people and it didn't work, which didn't make sense. You guys are really unlucky. But okay, so let's just do it. So how many people, and I know I asked this, right? How many people before, or how many people do we need to have a 50% chance, right? For two people to have the same birthday. Okay. Now we can kind of tie in things we've done. You think about this in ways of functions. Okay. Now this is on your test, so I'm assuming you guys are good with this now. But you think about this in way in functions, right? If we are going from, let's just say, so we're in a leap year, so we got 366 birthdays. Right, and let's say we want m people. So we're trying to find what m, right? What m we need for this. Well, you're mapping people, right? So you're going 1, 2, 3, 4, dot, 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 m, right? And there's, you know, January 1st, January 2nd, right? All the way down to December 31st. Right, we're thinking about functions, so mapping from the left to the right, mapping people to the birthdays. Okay, now how many functions are possible? Well, that first person has how many possible, right? How many options? I mean, they only have one birthday, but out of, there's 366 of them, right? Yeah, it's exactly that formula you have, right? N to the m, right? Now, that first person, there's 366, right? The second person, there's 366. The third person can be any one of those 366, right? So you get 366 for this m number of people. So we get 366 raised to the m power functions. Okay. Right, any questions on that part? So just how many functions there are? Okay, so now think about what we want in terms of functions. All right, you want two people having the same birthday, right? In functions, two people having the same birthday. So let's just make this the easiest way possible. Let's say the first person their birthday is January 1st. Two people having the same birthday, so that person will also be January 1st, right? In functions, what is this? Two birds going to the same hole, right? Two pigeons going to the same hole. That function is no longer what? not 1-to-1, right? It's no longer 1-to-1. So how many non-1-to-1 functions are there? Right, because in a sense, that's what you want, right? How many of those non-1-to-1 functions are there? Well, like a lot of the times is, let's count how many 1-to-1 functions there are, right? So there are blank number of 1-to-1 functions. Okay, this was also on your test, right? How did you guys do 1-to-1 functions? Right, well, remember we had, okay, I have 366 options, right? For the second one though, I used up one of the birthdays, so then I only have 365. For the third one, I used up 2 birthdays, so only 364. For the fourth birthday, right, I have then 363, and so on. Right, so it's what Barry has there, right? You got that n factorial, right? In this case, 366 factorial, right? Because you start at 366, right? Remember, you stop at when you run out of m's, right? So 366 minus m factorial, right? It depends on how many people there are, on how much down the line you'll go. Right? It's a permutation. Right? Any questions? So this is exactly what we've done, right? Really nothing new. All we're doing is applying to a group of people and then the 366 birthdays. We haven't even actually done probability yet. Okay, but putting this together, so then the probability of getting a 1-to-1 function, okay, your m can be, or your m is just the number of people, right? We're trying to figure out how many of those m's we need to have a 50% chance. Okay, so the probability of getting a 1-to-1 function, well, there's that many 1-to-1 functions divided by the total number of functions, right? So we get 366 factorial divided by 366 minus m factorial divided by the 366 to the n power, which simplified, you got fractions and fractions, which is never nice. But simplified, it's this. Okay, so this is the probability of you getting a 1-to-1 function, right? Remember, what we wanted was, right, we wanted 2 birthdays, right? 2 people with the same birthday, so that was not 1-to-1. So if this is 1-to-1, how do we find not 1-to-1? Yeah, it's 1 minus that. So 1 minus, and then that thing we have box there. Right, and that gives you, you know, if you have 2 people, so m, you plug in 2 for m, that's the probability that those 2 have the same birthday, and then 3, and then 4, and then 5. You plug all those numbers in. I don't know if your calculator can handle that. but then you end up getting that M should be 23, and that gives you a 0.506% chance. Okay, so it's just plugging in numbers after that. And you can test it. I don't know if your calculator will take it, but you can try it. So there is the probability function percentage. Yeah, you get 23. I think once you get to like 50, it's like 99% chance or something like that. Right, remember, to guarantee that two people have the same birthday, right? You got to think about worst case scenario, and that's that everyone has a different birthday. So you would need 367 people to guarantee that two people have the same birthday. All right, any questions on that one? All right, go take 10 minutes. We'll come back and we will do chapter 8. Feel free to ask questions if you have any questions. You could ask questions on your exam too right now. Also, please make sure that when you sign in into Zoom, you use your first and last name.
I actually had a question about the number of one-to-one functions.
Yeah.
So I was thinking it would just be 366 factorial, or why did we have to do a permutation?
Because if you like think about it on a smaller scale, so even like the one on your test, it was from 3 things to 8 things, right?
Yeah.
And you had like A, B, C, D, E, F, and then G, what is that, 7, H. So you had 3 to 8 things. Well, you had 8 options, right? And then you have 7 options, and then 6 options, right? It's not 8 factorial, right? It stops depending on the number of things you have. You see that?
Yeah.
So in this case, it would be like 8 factorial over 8 minus 3 factorial. That gives you the 8 times 6 times, or the 8 times 7 times 6.
Okay, that makes sense.
You're good, Joel. Joel, you have a unique name that you use, so you're good. Sorry, Paul, did I cut you off? Did you have a question? Another question?
Just to make sure that then you divide the whole thing by 366 to the m, because that's all the possible functions.
Yeah, so it's a probability now, right? It's the number of one-to-one functions divided by the total number of functions. Okay. Right, so this number divided by that number, which is this ugly fractions inside of fractions, but that just simplifies to that over here.
Okay, that makes sense. Thank you.
Mm-hmm. Anyone else have like test questions or anything? Yeah, if you miss number 4, the big O one, I think once you see it, you're gonna kick yourself about it. Cause it's only like 2 lines. Oh, thanks, Andre. The exam one, JP. So Andre says you can change the display name in your settings. Yeah, it's just like some of us have like common names, which I mean, you know, anyone can really just use the name that I got in the last one. That random person that showed up, they put their name as Nick, which is a common name, and I have a Nick in my stats class, but that was in my stats class, you know. Yeah, I can do the last one, GP. I'll just do it at the bottom. So that one was I forgot what the sequence was. Show that 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed is big O of n to the 4th. All right, so remember you need a constant. I labeled this as f of n. You need f of n less than or equal to a constant times n to the 4th. Thanks, Chris. So Chris has the step-by-step on how to change your name. Okay, so you got 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed. All that is less than or equal to changing all those things to an n, to n cubed plus n cubed plus n cubed plus ... plus n cubed. Right, for I guess I should have done k, but for n greater than, or no, n greater than 1. Greater than or equal to 1. Okay, now each one of those, you got n cubed, and you're adding it n times. So that's n cubed times n. So instead of adding, multiplying, which is n to the 4th. So your C is actually just 1. Yeah, I figured a lot of us are going to kick ourselves about that one.
Wouldn't you have been able to put the C as anything higher because it still would be true though?
Yeah, I mean you could, but I need to see the work on how you came up with that.
Right.
Which, yeah, I think some of us threw like some other numbers in there, but the way we got there wasn't necessarily correct. All right, yeah, the thing was, a lot of us try to use summations, but summations change depending on what your n is. Right, which then it doesn't stay constant. But yeah, you're right, just so you technically it could be any C. As long as you did it like a different way, as it worked. I mean, all those didn't have to be n cubed. You know, they could have been all 2n cubes. All right, 2n cubed plus 2n cubed plus 2n cubed. All right, and that gives you a different C value. It's just typically when we do it this way, we think about this being the smallest one that would work. Yeah, JP. Because we think about it being the smallest one that would work. Yeah, n to the fourth is greater than or equal to n to the third. Yeah, so your c ends up being n, which technically isn't a constant, right? Because it changes. It needed a little bit more cleanup because remember c has to be a constant number. N isn't constant because it's changing. Right, yeah, according to the definition of big O, so the definition we use, this one right here, remember c and k are constants. K is 1, c is a constant also. All right, so let's move on to chapter 8 then. That was the end of chapter 7. So chapter 8 is looking at the application and recurrence relations, which we've done. Right, remember recurrence relations are, you know, these like we had sequences before, right, where they come, you know, the term is dependent on the terms that come before it. Right, so, you know, this is something we've had come up, I think, in a couple sections now, actually. Okay, we saw this back in chapter 2 with some sequences, and then again in chapter 6, 5 with when we talk about Fibonacci sequences, right, and 5.3 with all the recurrence relations. Okay, so we're going to talk about that again. What we're going to apply to this section is some counting that we've done. Okay, so suppose that the number of bacteria doubles every hour. If there are 5 bacteria to begin with, how many are there after n hours? Okay, so let's just kind of build what this looks like, right? So this pretty much this whole section we'll use a sub n. So a sub n is the total number of bacteria after n hours. Okay, so let's label it as that. All right, so it's doubling every hour, right? So a sub n is equal to 2 times whatever there was before, right? So a sub n minus 1, right? The hour before, the n minus 1th hour. All right, any questions on where that came from? The notation or anything on there? Okay, so the first thing we can start off with is a sub 0 in this case. Sometimes you can't start out with a sub 0. What is a sub 0 in this case? It's 5, right? It's how many began, right? How many did we have when this first began? Right, well, there's 5 to start with. Okay. Then we do a sub 1, right? So after an hour, right, we know it's doubling, so we get a 5 times 2. So we get 10. We're actually going to be able to make this into a nicer formula than what we have over here on the left. Right? The second hour, so after the second hour, we have, well, we have a 2, right? We're going to match it up with this one. We have a 2 times whatever we had before. 2 times 5, which is 20. Now, if you write a 2 times 10, I think it's harder to see what the formula comes out to be. But this one works as well. But I want to show you, you can write it as a different way also. Okay. After the third hour, we get 2 times, right? 2 times, what did we have the hour before? Well, we had 20, right? But again, you're not going to be able to see it if you write 20. But let's write out all of this, which was the 20, right? So 2 times 2 times 5, right? Which is 40. Yeah, and I think Jacob got it, right? And you can see the pattern that will continue after that, right? You actually get the total number is equal to, well, notice that there's always just 1 5 in there, right? So we get a 5. I'm gonna match this up. So 5. What about the 2s? How many 2s are there? Well, we had 0 in there. We have 1 in there, 2 in there, 3 in there. So it's dependent on the n, right? So it's actually 2 to the nth power times 5. Right, so you get this nice formula here, which you know about exponentials and things like that, right? It matches up with that formula also that you have with exponentials. The a times b to the x power that you guys probably did in algebra. All right, any questions on that one? All right, so the next one is this rabbit example. So this rabbit example is kind of popular. You'll see why. So a pair of rabbits are put on an island, one of each sex. A pair of rabbits does not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produces another pair each month. Find a recurrence relation for the number of pairs of rabbits on the island after n months, assuming no rabbits die. Okay. So I don't know if have you guys ever had rabbits before? They breed like crazy, right? So let's just assume in this one that no rabbits are going to die, just so we can see what that is going to look like. So your book makes a nice table with pictures and everything. I'm just going to make a regular table. So we have different cases here, right? We have pairs that are less than 2 months old, right? So these are the ones that are not going to breed. We have pairs that are at least 2 months old, right? So those are going to breed. Then we're looking at the month, and then what we want is the total number of pairs. So total number of pairs. Right? So let's just say they throw 2 rabbits on the island, right? They're let's just say they're newborn, right? So in this case, you have 1 pair that is less than 2 months. We have 0 pairs that are at least 2 months. This is the first month, so we have 1 pair. Okay, the beginning of the second month, they're not 2 months old yet, right? They've only been 1 month. They got to wait until the second month. So we still have 1 pair. We have 0 that are at least 2 months old. This is our second month. We still only have 1 total pair, right? But now beginning this third month, you'll see that that 1 pair is going to be able to breed and have 2 more rabbits. All right, so now beginning of the next month, this 1 pair now is going to move over to this column, right, because they are now at least 2 months old and they breed a new pair. So this is the third month, and now we have 2 pairs of rabbits. Anyone know what this sequence is going to look like?
Not Fibonacci's.
Yeah, it's going to be Fibonacci, right? So now let's move on to the next month. Okay, so the next month, this pair right here is going to make another pair, right? Now this pair right here is not old enough yet to move on to the next column. So we're going to have 2 pairs in that first column. We're still going to have just 1 in there, in that second column. This is the fourth month. And now we have 2 plus 1. We have 3 total pairs.
So why just the second row? Why we have 1 again?
In the second row, in this one?
Yeah, no, the pairs are at least 2 months old.
This one?
Yeah.
Because you still only have this 1 over here, right? This one was just born, so they haven't moved over yet. They're only 1 month old. They're not 2 months old.
Okay.
Yeah.
I see.
Okay, and we'll do 1 more row, but yeah, a lot of you said it right. You got the 1, 1, the 1, 2, the 2, 3. All right, it's looking like Fibonacci. So let's do 1 more. Okay, so now this is where it starts to get a little confusing because you got to remember what was in what. There is a pair in here, right? It was this one that is now going to be old enough to move over here, right? So we had 2 now in that second column, right? Which left you with 1 over here, right? Taking away 1, but now each one of those pairs produces a new one, so you actually get 2 more, and you get 3. So the fifth one. So now you have 5 total pairs. And it gets to be a little bit more there's organization after this. So you got to remember which ones are which. Your book does it nicely with actual pictures of rabbits. It just would take me a long time to draw all the rabbits. But you can start to see what the pattern would be. It is Fibonacci. All right, so the way this would look is, if we just label with Fibonacci, well, f of 1 is 1, f of 2 is still 1, right? This is after n months. So we know that it's going to be the previous one plus the one before that one. All right, so that's a cool application of Fibonacci that comes up. All right, Fibonacci comes up in a lot of places. All right, any questions on that one? All right, cool. So next example. So find a recurrence relation and give initial conditions for the number of bit strings of length n that do not have consecutive zeros. How many such bit strings are there of length 5? Okay, so initial conditions, I don't know if we've actually used that term yet, but initial conditions are like these values here, f of 1 equals 1, f of 2 equals 1. Your initial condition in this first, the bacteria one was this a sub 0 equals 5. All right, you need a starting point somewhere. Right, that's what your initial condition is. All right, so we're talking about bit strings, right, of length n. So I mean, we don't really talk about length 0, I guess. So I mean, the first thing we would have, I'm gonna label, so a sub n, let's say, is the number of bit strings of length n that do not have, and then in this case, consecutive zeros. So consecutive zeros are zeros back to back. So like 2 in a row. All right, let's start off with n equals 1. Okay, so we got length 1. How many bit strings of length 1 do not have consecutive zeros? Yeah, 2. It's both of the length 1 ones, right? You got the bit 0 or the bit 1, right? Neither of those have 2 consecutive zeros. Okay, what about n equals 2? So how many of length 2 do not have 2 consecutive zeros? You can actually write all those down. Yeah, it's 3. Because there's 4 options when you have 2, right? You can have 0, 0, 1, 0, 0, 1, or 1, 1. Right? This one doesn't count because you got the 2 consecutive zeros, so only those 3. All right, and then those are going to be our initial conditions. Okay, and you'll see why. Okay, so I don't follow the way your book did it. Now, I think there should be different ways to do this. Okay. You basically have two cases, right? All right, so we have two scenarios. A bit ends in 1 or ends in 0. All right, that last number, right, has to be a 1 or a 0. Right, strings that end in 1 are these strings of length n with a 1 at the end. Okay, so you got some kind of string here, right? However long it is. That last spot on there is a 1. Okay, now the way you kind of think about this is you kind of go back to our counting. Right, when we go back to counting, well, how many do we have? Right, well, it was n spots, right? But that last one, we forced a 1 in there, which leaves us with how many spaces? So how many spaces? Yeah, n minus 1, right? Because we started off with n. That last spot, though, we forced a 1 in there. But we still have n minus 1 spots, right? So actually what this is there are a sub n minus 1. All right, we're looking at all the ones of length a sub n minus 1. All right. The second case is the same thing, but now you end with a 0. So strings that end in 0 are these strings of length n with a 0 at the end. Right, but if you have a 0 at the end, what does the second to last one have to be? So now instead of having a 1 at the end, let's say we have a 0. Yeah, the second to last spot, it can't be a 0, right? Because we don't want we want how many don't have. So that has to be a 1. Right, so strings that end in a 0 are the strings of length 1 with the 0 at the end and a 1 in the n minus first spot. Right, how many of those are there now? Well, same idea, right? We had n spots, but now we forced the last 2, which leaves us with how many spots? N minus 2. So there would be a sub n minus 2 of those. right? And by breaking it up in these two cases, right, you know then that the total number is equal to, well, however many of these there are, a sub n minus 1, plus however many of these there are, a sub n minus 2. And the nice thing is that doing it this way, right, I kind of cheated and did our initial conditions first. But once you get to that point, you got to ask yourself, okay, well, where do I start? Well, I see two terms here, right? That means I need two starting points. Which are these two starting points? Kind of an interesting way to do things, right? Yeah, it's gonna end up being Fibonacci without the ones. Yeah. Right, because so you did a sub 1 and a sub 2. So this one is going to hold for greater than or equal to 3, right? Because you have 1 and 2 up here. So if you plug in 3, you get 3 minus 1, 2. 3 minus 2 is 1. So you get those, right? So I'm going to squeeze it in here, but a sub 3 is going to be a sub 2 plus a sub 1, which are initial conditions. So 3 plus 2, that's 5. How many did we ask for? Bit strings of length 5. Okay, so we got to go up to a sub 5. Then a sub 4, so plugging in 4, you get a sub 3 plus a sub 2. That would be a 5 plus a sub 2 is 3. That's an 8. And the last one, a sub 5, that would be a sub 4 plus a sub 3, which is 8 plus 5, and that's 13. So we'd get 13. And it is, like Willie said, Fibonacci again. Any questions on that one? All right, so let's do, this is the last one from this section. So find a recurrence relation for the number of ways to climb n stairs if the person climbing the stairs can take 1 stair or 2 stairs at a time. And how many ways can this person climb a flight of 8 stairs? Okay, now, depending on how you see this one, you can start with either 0 stairs or 1 stair as your initial condition. But either way, so let's say let a sub n be the number of ways to climb n stairs. think you're off by a little bit, Misan. Okay, so let's kind of think about this actually with let's build up to this one. N equals 1. So if you only have one step, I guess, how many ways can you climb that one step?
Two ways.
It's actually just one, right? It's just climbing that one, right? Because remember, you can either take one stair or 2 stairs at a time, but there isn't even 2 stairs, so you can only do one. All right, what about when n equals 2? So how many ways can you climb 2 stairs? Two ways, right? You can climb that 2 ways. Either you go 1 step and then 1 step, right? 1 and 1, or right, we have the option of doing 2 stairs at a time, so that would be or 2 steps. All right, I'm actually going to do a little bit more so we can see this pattern. About 3 steps. How many ways are there to do that? It's 3. Right, so in this case, you can go 1 step, 1 step, 1 step. Right, you can go 1 step and then do the 2 steps. Right, or you can start off with doing 2 steps and then 1 step. All right, any questions on those 3? Think about and try 4th step. So if you have 4 steps, how many ways can you do that? Now, if you see the pattern already, you can easily come up with it. Think about why it is that pattern. It's a little bit more than 4. I'm seeing different answers, which is good. So we're all thinking differently. I think yeah, Jacob, it is 5. And there are 5 ways to do it. Okay, now if we have more than 5, we probably have some repeats in there, right? So 4 steps. All right, so let's write these out. So I can either go 1 step, 1 step, and then hop over 2 steps. Right, and I'll show you why I'm writing it down like the way I'm writing it. We can do 2 steps and then hop over 2 steps. All right, that will give us 4. Okay, we can also do 1 step, 1 step, 1 step, 1 step. We can go 1 step, 2 steps, 1 step, and 2 steps, 1 step, 1 step. All right. For those of us that got less than 4, we see our missing ones. And for those of us that got, or sorry, less than 5, we see our missing ones. And then for those that have more than 5, we see the repeats, double counted. Yeah. Okay. Now think about this, right? Anyone see the pattern? Now that you see it being 5, Fibonacci again, right? You got that 1, 1, 2, 3, 5, right? So you can tell me then what is this one? 8 stairs would be, right? By going on and on. Now, how do you get that, right? It's almost the same thinking as the one we did above, but I'm kind of doing it a little bit differently. So we can see this one. All you really got to do is, okay, with 4 steps, right? Think about, we had this already for us, right? We did the number of ways to get 2 and the number of ways to get to 3 stairs, right? If we are on the second step, right? So this right here is representing us being on the second step, right? Because we got to 2 stairs, right? It was these 2 ways, right? How do we get to the 4th step? Right. Well, we could do, and let's just say straight to the 4th step. Right. Well, in this case, from here, I could jump over 2, which is that one. And from here, I jump over 2, which is that one. Right. So that's from the second step. How many ways? What about if we were on the 3rd step? Well, if we were on the 3rd step, right, we had this way, this is how we could get to the 3rd step, right? We would need 1 more, right? This is another way of getting to the 3rd step. Well, we would need 1 more. And this is another way of getting to the 3rd step. We would need 1 more. All right, so all I really did was look at those previous 2 and added 2 at the end or added 1 at the end. Right, this one doesn't apply because you can't go from the 1st step to the 4th step with 1 move. Right, the one you'll do in your homework, you'll be able to. It's going to be 1 step, 2 steps, or 3 steps. Right, but in this case, it's only 1 step or 2 steps at a time. All right, everyone see that? Are there any questions on that? So putting all this together, we get a sub n is equal to a sub n minus 1 plus a sub n minus 2, right? The 2 previous ones, which is a Fibonacci sequence, right? It depends on what you start at. Now, in this case, we started at the same values we would have, right? The 1 and the 2. So to get the, let's see, what did we get to? We got to, let's skip some. We got a sub 4. That was a sub 3 plus a sub 2. That was the 2 plus 3, which is 5. Yeah, it's just like, yeah, I like this approach because you can see the things, all right? Sometimes it gets to be a little messy though, on, depending on what you're actually looking at. Right, like the bit one above, if you would have gone to the 4th one, you'd have 2 to the 4th, so you'd have 16 to write out and see which ones don't have a double 0, which then it gets to be a little messy. Right, but if the numbers aren't big, you can always write them out and start to look for patterns. So then a sub 5 is going to be a sub 4 plus a sub 3. So that'll be the 5 plus 3, that is the 8. You're going to start to see the sequence come into play. A sub 6, that's a sub 5 plus a sub 4. That is your 8 plus 5. That is 13. Remember, we want for 8 flights of stairs. A sub 7, you want a sub 6 plus a sub 5. That'll be the 13 plus 8. That's the 21. And then squeeze in the last one. A sub 8 is a sub 7 plus a sub 6. 21 plus 13 is the 34. All right. Any questions on any of those? All right, cool. So on Wednesday, then we're still just one section behind. I'll catch us up at some point. Yeah, we're just one section behind. We'll do 8.5.